You've maybe heard that if you are stranded in the ocean, you should not drink seawater, right? Because it actually causes you to become dehydrated faster than not drinking anything. So it's kind of a rough situation to be in where you're surrounded by water, you're horribly thirsty, but you can't drink any of the water because it'll make you more thirsty. And osmosis explains why it does that. Osmosis is the flow of a solvent from a less concentrated solution to a more concentrated solution. And this happens when you have a solution with a high concentration of solute, and it's going to pull the solvent from a lower concentration of solute. So let's look at a picture. Seawater is sometimes described as a thirsty solution. Here's an illustration of your intestine. Here's your intestinal wall. And this is the outside of the intestine, which is inside your body. And this is inside the intestines, which technically is the outside of your body. Did you ever think of that? You've got this long, squiggly tube running through you, right? Technically, that's on the outside. Yeah, think about that for a while. Anyway, if you drink salt water, you've got a lot of sodium and chloride ions in your intestines. And you have less sodium and chloride inside your cells. And what happens is, the water is, the way I think of it is, nature likes to equalize things. And you have a low concentration here and a high concentration here. Nature doesn't like that. And so water molecules will move from the low concentration to the high concentration in an attempt to dilute this solution, to make it more dilute. If you add more solvent, you dilute the solution. And so it's trying to get these two concentrations equal. Now that's the personifying molecules or whatever approach. That's not very scientific. But the membranes in your cells allow water to pass quite freely, and they do not allow the sodium and chloride to pass as freely. And so the sodium and the chloride can't go back and forth across this membrane, but the water can. So by having a lot of sodium and chloride in your intestines, it actually pulls water out of your body tissues. And so instead of getting hydrated, you become dehydrated by drinking salty water. Here we have a U-shaped tube. We used to call them U-tubes, but now that means something else. So a U-shaped tube, and we have a semi-permeable membrane in the middle. If we put a saltwater solution on one side and pure water on the other side and leave it alone for a while, we see something rather strange happening. We see the water level on the salty side go up and the water level on the pure water side go down. This is not something that normally just happens, right? If you have a curved tube and you've got a liquid in there, usually it's the same on both sides, right? And so this will happen all by itself. What happens is that we have water molecules moving from this side to that side. Can't see the arrows there. We can explain this, I think, best in terms of equilibrium. And your book doesn't talk about that because in the book they haven't gotten to equilibrium yet. But here we have a lot of water molecules, and here we have fewer water molecules. And the water molecules can go back and forth across this membrane. These blue circles cannot. And so at first you have a lot of water going across just because there's more of it. Remember, higher concentration will cause the reaction to go in a forward way. So higher concentration here will cause this reaction to go faster. After a while, as this concentration, as the amount of water on this side goes up, then you're going to see an increase of the water going back the other way. But the water amounts, the water concentrations are not the same on both sides, and so overall it will continue going this way until it gets to a point where the pressure here causes this to be equal. So there's a pressure difference. When we talked about gases, we learned that when we see a difference in levels of liquid in this tube, that indicates a pressure difference between the two sides. So this will only go so far before it stops because of the increased pressure on this side. And this pressure is called the osmotic pressure. If you have more solute in this, it will go higher. And so the osmotic pressure is related to the concentration of that solution. Have you heard of reverse osmosis water purification? They advertise that a lot on the radio and television. This is osmosis, where water moves from a lower concentration or from a pure state into a, you could think of it as contaminated state. Reverse osmosis does the opposite, and it does that by adding a pressure here. And if you pressurize this side, you can force the water to go through to the other side. And that's how reverse osmosis works. Osmosis is a colligative property. It depends on the concentration of the solute particles. Doesn't matter what the solute particles are. So all of the membranes in your cells act as semi-permeable membranes, meaning they allow some things to pass and not other things. If you put any living cell in seawater, very salty water, it's going to lose water because of osmosis and become dehydrated. And here's some pictures of what can happen to your blood cells. So in medicine, they're very concerned about solute concentrations when they give you IV fluids, because they're putting a solution directly into your bloodstream. And so it's really important that it not cause problems. So these are some words that are used in medicine: isotonic, hypotonic, and hypertonic. Iso is a prefix that means the same. Think of an isosceles triangle. The two sides are the same. Isotonic means that the concentration of the solute in the surrounding fluid is equal to that within the cell. And if we have red blood cells in an isotonic, isotonic solution, then there's no net flow of water into or out of the blood cells. And so they're fine. Hypo is a prefix that means below. Now the surrounding fluid is lower in solute concentration. Here's a picture of blood cells in pure water. Well, the concentration of solute inside the blood cell is higher than the pure water outside. And so water will flow through the membrane into the cells, causing them to swell up. And if you let that go on long enough, they'll actually burst. Would that be a good thing to be happening inside your bloodstream? No, this would be a bad thing. If you have too much salt, hypertonic, too much solute, then you have a dehydrating effect, and water flows out of the red blood cells, and they crenate, and they crinkle up on themselves, and that's also not a good situation. So when they give you an IV in the hospital, it's generally a 0.9% sodium chloride solution, which is isotonic with your blood. And that way it's not going to dehydrate you, and it's not going to cause your blood cells to shrink or explode, which is, a good thing. And that's the end of chapter 13. This solution-dilution equation, only use it for dilution. Do not use it for solution stoichiometry. Don't. Just don't go there. Chemical skills